Hi, we're back. And this one was a little bit different because I wanted to get into laboratory work, experimental work, and in particular, data analysis. And, you know, what students learn from, say, middle school through the high school for science labs is typically that if you're making certain kinds of measurements, whether it's times or distances, speeds, temperatures, whatever, is that whenever possible, you want to try to take multiple trials, multiple measurements of the same quantity. And there's a reason for that, is because you rarely get the same measurement twice when you do something. Even if you're using the same tools, the same procedures and methods and techniques. And it's just the nature of data collection. So what students have been told is to do trials and then find the average value and to go with that average. It's exactly the right thing to do, whether you're in middle school or whether you're a Nobel Prize winning scientist. The thing is, many science teachers often leave out what I consider to be the single most important part of any experiment, and that's error analysis. It's thinking about how good is your data. And there's one quantity in particular that can be used to find out what we call the uncertainty when you do a certain number of trials for a particular measurement. And that's called the standard deviation. It has its own symbol because it's used endless times in experimental work. It's the Greek letter sigma, lowercase sigma. And this is the weird, funny looking definition if you were to write it out in symbols. Basically what it's doing is it's taking the average value. Maybe we're doing time trials, okay, in a physics class. The average time, we want to look at how close each individual trial, each individual measurement is to that average. And we're looking at that difference. How close is it to the average? Now, the average itself is, in probability theory, the most likely, the best answer, the best result, the most likely result. Okay, it's really in terms of probabilities. We're going to square that quantity in our numerator and then add all of those terms together. And we'll throw some numbers in here so you can see what this looks like if you were to write it out. Now, the n down here is the number of trials. This is the actual reason why the more trials you do, the better you understand your data, the better the results, the more believable it is, that kind of thinking. When your teachers tell you that, they probably don't put it in this term, but that's the reason the number of trials is a good thing. It's reducing the uncertainty in your experimental measurements and the succeeding results that you get from those data. Now the sigma, the origin of this is kind of interesting. It comes from the bell curve. That's what most people know this particular function by. Technically, the bell curve is produced by a Gaussian probability distribution function. It's really just how the spread of data, when you have lots of data for a given measurement of a given quantity, it naturally forms this particular kind of curve that so many people have seen and talk about. Let's just see what this looks like and how it works. Suppose that in a physics class, you're measuring, you're letting something roll by at the same speed every time. You're trying to determine its speed, so you measure the time to travel a certain distance. Maybe you do 5 trials, 5 individual measurements. You go ahead and you take the average. Now I'm actually going to do something here to this average, the way I present it. I'm going to round it off to the hundredths place. Now the reason for that is, if I'm using a stopwatch like on your cell phone or just a normal stopwatch, usually they're good down to 100th of a second, kind of like these measurements are shown here. Well, the average needs to be rounded off to the hundredths place then. That's the level of precision that you're getting from your actual tool, okay, a stopwatch. And anything less than 100th of a second, you can't report that because you don't know. You can't measure it. Okay, you just be guessing. So you only want to take it down to that level of precision that you can really measure the thing with your device. Now, according to this definition of standard deviation, I want to take this average, 0.96 seconds, and I want to find the difference with each of the 5 individual measurements, okay, the trials that we have, and then square that number. The summation symbol here tells us we're going to add all of those numbers together on top in your numerator. This is what it would look like if you wrote it out. Okay, 0.96 minus the 0.9, which is your first data point. We're squaring that. Then you take that difference with the second, difference with the third, with the fourth, with the fifth. There's just numbers on top now. And we're dividing it by n minus 1. Okay, we have 5 trials here. So 5 is our n value. Let's subtract 1. All of this is under that big old square root. And if you punch this into your calculator, this is the answer that you get. Now, this actually would have units of seconds. So it has the unit of whatever measurement you're making. We're going to round this off as well when we report this in a lab write-up or something. I'm also going to round that to the hundredths place because, again, we can't measure anything less than that. So we would just be guessing. Okay, we're going to be a little more conservative with it. Why do we do this? What does this mean? Okay, so this formula pops out a number. So what? Well, the importance of this number, of the standard deviation, that's the plus or minus of your average time. This gives a measure, a way to quantify the spread of your data, of your measurements. Okay, notice, you have a low of 0.87 seconds up to 1.09 seconds. And that's pretty typical if you're doing a stopwatch in a high school science class. You see numbers and it's spread like that. Well, this is the right way to quantify it. And this uncertainty tells us something more about the data that we're using to try to figure out the result and to figure out our conclusions based on these data. So when you look at standard deviation, this is a bell curve. Notice here's the sigmas down along the x-axis. 1 sigma, plus or minus 1 sigma, 2 sigmas, 3 sigmas. And they've got these percentages drawn on these areas of the curve. These are probabilities. Okay? So if we're going to report that the time we think it took this little thing to move past us, took 0.96 seconds to travel a certain distance, plus or minus 1 standard deviation gives us the shaded region here of the bell curve. We have this Gaussian. And according to this diagram, that's about 68%. What does that mean? Well, what that tells us is that there's a 68% chance, this is probability, there's a 68% chance that the actual time it took this object to move that certain distance is within this range between, if you subtract the standard deviation to if you add it to the mean. So 0.87 seconds up to 1.05, 68% chance that the real actual measurement is in that range. What if you go out to 2 sigma? What if we add more area here? Well, according to this, we're adding another 13.6% on both sides. Okay. So now we're up to about 95%. There's about a 95% chance that the actual real time, remember, there is no such thing as a perfect measurement. We never know if we measured the real time or the real anything. It's just a probability, best chance of measuring it. Because there's always this spread when you do the trials. Well, between 0.78 and 1.14 seconds, 2 standard deviations out in both directions, there's a 95% chance it's in that range. Go 3 standard deviations. Now we're up to about a 99% probability or a 99% chance that you're in this larger range of 0.69 to 1.23 and so on. So that's why uncertainty, understanding the standard deviation and other quantities related to it, is the most important thing. It tells us how reliable our data are. What kind of range are we talking about? Is it so big that we really can't make any conclusion? Or is it really narrow? And we have a really good understanding of the experiment and the results and conclusions that we can have. It's all about this width. It's, how big are these ranges? So the results, well, that's kind of what we're after ultimately. Those are easy to find. That's like average values and stuff like that, throwing them into an equation and popping out a number. That the real work in scientific experimentation is done trying to figure out the uncertainties, trying to do the error analysis, understand how good your data are, and what kind of conclusions you can gain from them. So I hope that this makes some sense. If you're new to this, pictures like this are probably just kind of mind-boggling and confusing looking, and that's understandable. But keep in mind, we can get these numbers, we can interpret them, and we can get a better sense of how good our experiment actually is, and what kind of results and conclusions we can draw from those. So this is just an introduction, and I hope it helps. And until next time, we'll see you later.